Wait. So it just means that test number 3 is going to follow test number 2. Test number 3 is online. It doesn't have the same weight, and it's open notes, and it's going to be what we are doing now. So you need 6, and then conservation of energy as well. So you need 6 and 7. It's going to be online. I will open like a 4 hours window just for people who have a job or this and that, but it should not be more than 1 hour. Okay? I need to look into it. So I forgot the date, but be prepared for that. We still don't have the date for the final. It's not my fault. Like every semester, they forget this class. Every semester, I email them, and every semester, they take forever. So just bear with me. As soon as they get back to me, I will let you know. So last time we talked about the universal law of gravitation, and that will be the force between two masses, right? So if you have a mass m1 and m2, so that could be the Earth, that could be the Moon, or that could be the Sun, and that could be the Earth, or that could be the Earth, and that could be you. So you have an attractive force, which is inversely proportional to the distance squared. And we talked about that. I just want to clarify one thing. Are you with me? I miss. Okay. So you see here, if you have the Earth, so let's say you have the Earth here, so that will be the mass of the Earth. Okay. And then you have a mass here, m2. So the force between the two masses, it's going to be that constant here, which is very small, times the mass, Hello, the mass of the Earth, right, times the mass m2 over the distance square. And that distance will be between here and the center of the Earth, right? So that will be the distance r. And the Earth has a radius r. Okay, so that will be the distance. We always take the distance from the center of the Earth. Okay, because everything happens like all the mass was concentrated here at the center. Okay, so one way to look at it, so we're going to say the force here equals G. Now this here depends only on the Earth, right? So that here, that's what we call the gravitational field. That expression here is called the gravitational field. And then you have m2. And then I did a mistake, forget. Let's go back. So you can write down that F, the gravitational force, equals m2 g. So this is g. And g, this is called the gravitational field. Magnitude. So the magnitude of the gravitational field. Okay. Example, if you are located on Earth, so now if m2 is here, so that will be you. So then the gravitational force here is going to be G, okay, times m2. And you can do the computation here, that will be 10. So it will be m2 times 10. So that will be your weight. Okay, if the distance from the center of the Earth is just the radius. So we did that last time. Do you agree? We did compute that the acceleration to the gravity equals G, okay, times the mass of the Earth over the radius of the Earth squared. So this is called the gravitational field. as you move away from the Earth, the field is going to decrease as the square of the distance. And I told you it works the same way for light or radioactivity, radiation, right? Or light from the sun, for example. Okay, so it's going to decrease, the magnitude is going to decrease as the square of the distance, and it's called the inverse square law. Now, we can say that the Earth here is generating a gravitational field. So it's like an aura. Okay, so we can define here the gravitational field. So we have the magnitude, but you see the gravitational field is actually a vector field. So it means at any place in space, you can define the vector G, right? And the magnitude of G, it's going to be this. Okay, so this is called a gravitational field. And the way you can look at it is saying if a mass is placed into that vector field, it's going to experience a force, and that's going to be the force. Okay, so you can think of that as a source or a sink. Like if you take advanced calculus or fluid mechanics, that will be called a sink, meaning it's generating that gravitational field around. Okay, it's like a source for this field here. So if I look in Google, okay, so if I tap, this is fun. Did you try this one? That's Pac-Man. That's my time. Gravitational field. You can see what it looks like, right? So the Earth is making this aura around it, and it's called a gravitational field, such as if there is a mass into that field, it will experience a force. The magnitude of that field is given here. You see, it's going to be that very small constant, the mass of the Earth, and that will be the distance between the mass and the center of the Earth. Okay, you can think of the field as a force per unit mass. You see here, force per unit mass. Okay, the gravitational field, the magnitude, you can think of that as the gravitational force per 1 kilogram. And the magnitude, okay, it's going to be that very small constant, the mass of the Earth and the distance from the Earth. And the distance has to be taken from the center of the Earth. So this is a very nice picture. That's why I'm using Google. It's showing you the gravitational field, and it's going to be 1 over r squared or 1 over x squared. You see here, that's 1 over x squared. And if you place the moon into that field, it's going to experience it, and that will turn into a force toward the Earth. And then Einstein came, put everything upside down, and then he said there is no force, right? It's just the Earth bending the space-time like a trampoline, and then the moon is just trapped in one of these curves, right? But thinking of Newton, using Newton, that's enough to go to the moon. Okay, so this is what we call in vector calculus, it's a vector field, because anywhere in space, I can define that vector, so that will be the magnitude, and the direction is toward the Earth. Any question? Okay, so that equation here, so let's write down somewhere. Okay, so we have, that's going to be for the pop quiz or assignment. I forgot. So anyway, for distance equals or greater than the radius of the Earth. Okay, you see that the magnitude of the gravitational field is going to be G, the mass of the Earth, and the distance to the center of the Earth. If R equals R, G is just equals to 10 meters per second. And if you are inside the Earth, then we can show that G will be proportional to R. So it's not inverse anymore. Okay, we're going to worry about that in one of the assignment or pop quiz. Okay, so that's just a parenthesis. Gravitational field. Okay, so we did that. If you have any question, let me know. So inverse square law, very important. We discussed that last time. That will be the potential energy of a mass placed inside the gravitational field of the Earth. So if you are on Earth, we can just say the potential energy is just mgh. Okay, so just mg, g is 10, h is the height. It's relative to a level 0. And as you move away from the Earth, you see it's gonna get to 0. So the potential energy, that will be the real equation. You see the potential energy is negative because it's binding. So it means if you have a mass here, it cannot escape the Earth. It wants to go back to the Earth, right? All that potential energy is going to turn into kinetic energy. That's why it's binding. So it's important in chemistry as well. So I don't know if I have hydrogen atom. Hydrogen atom somewhere. Here. So you learn that in chemistry. You see, if you take the hydrogen atom, so the molecule hydrogen, it's two atoms of hydrogen and they are bound together. Okay, they are bound together. So they have negative potential energy because it's binding. And they are very happy. So that will be the distance between the atoms. If you try to squeeze them, you're going to have a restoring force that will push them apart. So that will be a repulsive force. You see that the slope is the restoring force, but it's minus the slope. So you see here the slope is negative, so the force will be positive, pushing to the right. If you try to pull them apart, they get also upset. Okay, so you see the slope is positive, so the force will be negative, pushing to the left. So it will be here, it will be repulsive, and here it will be attractive, and here you have the lower level of potential energy, so it's gonna be happy. Okay, so that will be for the hydrogen molecule, and that's how it's used in chemistry. Okay. Okay. So these are examples of potential energy. You're going to see next semester you have electric potential energy as well, and you have elastic potential. We already talked about that. When you are doing work on a spring, so if you stretch it or if you compress it, all the work that you are doing will be stored in elastic potential energy. And there is a restoring force. So you take the derivative and you get kx minus kx, right? So a restoring force derives from potential energy. So this is called a restoring force because it wants to restore to the initial configuration and you can get back the energy. And then I don't know why. Oh yeah, I think that's gonna be for the pop quiz. So I just want to show you this. This is fun to play with. Here, uh, Here I have gravity. Gravity. I don't care about gravity. Okay, let's forget about gravity. So you see here, it's called a simple harmonic motion. And what I want to show you is the relationship between the acceleration and the restoring force. You see, acceleration, remember for the test, is the net force per unit mass. Acceleration has always the same direction as the largest force. And you see the acceleration here is the largest when the restoring force is the largest. And then here, when it goes through its equilibrium, there is no more restoring force, there is no more acceleration, but it's overshoot. It overshoot. So it keep going. So what's happening here? You are switching back and forth between elastic potential energy kinetic, elastic potential energy kinetic, elastic potential energy kinetic. Okay? So this is called a simple harmonic motion. And when you have a simple harmonic motion, the restoring force is proportional to the displacement. The restoring force equals K times X. That's called Hooke's law. Okay? So the restoring force, which is called the strain or stress, the strain is proportional to the stress. That's Hooke's law. Okay? And when you disturb it, it will start to oscillate. Simple harmonic motion. Okay, so that's for the pop quiz. Okay, so now let's define power. So power involves time. Work does not involve time. So if two students, they don't have the same mass, but no, they do have the same mass. Sorry, they do have the same mass. One is taking the elevator, the other one is taking the stairs, and they get to the same height. The work done against gravity will be the same, but the time is not the same. So power is the rate at which energy is consumed or energy is produced. So a Ferrari, for example, has more power than my Hyundai. My Hyundai is like 30 horsepower. A Ferrari, I don't know, is 800 horsepower. So you see, it's going to consume energy at a higher rate. And that will be the definition. Okay, it's going to be work divided by time. Work is energy in transfer, but how quick energy is being transferred. And work is also the change in kinetic energy. Okay, so some examples here. Sleeping, of course, you're not consuming or burning a lot of calories here. Biking, so the unit is in watt. Okay, so if you are using, so it goes like this. So the power in watts is the work or the energy, the change in energy, that will be in joule over the time in second. Or you can also say it's a change in kinetic energy over the time. Or for short, you can say power is energy over time. So it depends on the unit you are using. If you are using the unit joule, so the energy of the work is in joule, then you want your power to be in watts and the time has to be in second. But when you are paying your electric bill, they don't use joule because joule is a small unit. Then people will panic if there's all of a sudden see that they have spent, 10 to the 6 or 10 to the 9 joules. So they don't use that unit. They use a larger unit, which is the kilowatt hour. But it's still energy because you see you have power and you have time. But if you are using this unit of kilowatt hour, Then you want the power in kilowatt, and you want the time in hour. Okay? And of course, 1 kilowatt is 1,000 watts. It's what? No, there is a joke again. It's what? It's what? 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 So it's what? Okay? Um, so 1 watt is 1 joule per second. 1 joule, it's energy, so it's force times distance. So, and the force is mass times acceleration. So mass times acceleration times distance divided by the time. So that will be the SI unit. We call that the watt, James Watt. During the Industrial Revolution, he was working on making the machine as efficient as possible. And when they were 19th century, at the end of the 19th century, beginning of the 20th century, they were building the first automobile, but it was very hard to convince people to switch from their horse to an automobile. So try to convince them. They came up with a new unit here for power. They came up with that unit here, which is called 1 horsepower. So that will be the energy that a horse can produce in a few minutes. We can produce as much as 1 horsepower, but for a very small time. Like when you do heat, high intensity training, whatever, very small time, you can do one horse. Okay, so at the time, the first automobile, it was like 1 horsepower. So they would say, okay, why don't, horse cost a lot of money. Why don't you switch to automobile? It will be the same. And then in the 20th century, they make the automobile more efficient. So a small car today is like 30 horsepower. A small Hyundai Venue, about 30 horsepower. I say that because that's what I have. A Ferrari is 800 horsepower. The beautiful one, the very expensive. You see a lot of them around here. So 800, 30 to 800. So 1 kilowatt hour is a unit for energy as well. And you can convert that into joules. And people don't know how to deal with scientific notation, so that's why when they're going to bill you, they're going to use kilowatt hour. Is that clear? Okay, so that comes from the book Physics for Future Presidents. Very interesting. If you like engineering or physics, I highly recommend this book. It's not heavy in math, but you learn a lot. So anyway, 1 watt, just to give you an idea how fast energy is burned. We are 1 watt flashlight battery. 100 watts is for us. We consume about, on average, depend if you are old or if you are an athlete will be more. We spend 100 joules per second, right? But remember why if I touch you, I'm not going to burn myself because that energy is spread out over a large area, even though it's the same amount of energy per second. And then 1 horsepower for someone doing heat. So this is also interesting. 1 kilowatt, you need 1 kilowatt for a small house. So solar energy is good for a small house. It's not good for a whole city. Okay, 100 horsepower for a small car, 1 megawatt. So you multiply by 1,000. Mega is a million. Okay, so a million here for a thousand for a small house. So if you have a 1,000 house, that will be 1 million watts. So 1 megawatt. A city of 1 million people, you need 1 gigawatt. So that's why nuclear power is very efficient. For the same mass, you get 1 million times the energy that you get if you are burning fossil fuel. And forget about solar energy, it cannot supply. It didn't work. In Germany, they tried. You have all those ugly wind turbines. It destroyed the landscape, it killed the birds, and it's not efficient. And they had very quietly to come back to mining for coals, and coal is very, very, very bad pollution, right? So anyway, let's go back. Okay, so let's try this one. So that was back then 10 cents per kilowatt hour. Let's see how much you're gonna pay. So now in Miami it's 15 cents, which is very, very cheap. New York City is twice that much. Hawaii is 40 cents. So for electricity, of course, the issue here is that you have to use AC, right? But anyway, let's do the computation. So you have 10 cents per kilowatt hour. You are using a 800-watt microwave and you use it for 2 hours. I don't think it's a good idea to use it for 2 hours, but let's say everything will be very dry, right? Just for the sake of the computation. Don't stare. Do. Energy kilowatt hour is power in kilowatt times the time in hours. Yes, 16 cents, you're right. Yes. That was back then. Now it's a little bit more expensive. It is 15 cents. But 15 cents is very cheap. Except that we have to use the AC. I mean, some people don't. Some people use fan, which is good. I can't. Okay, so the energy in kilowatt hour is the power in kilowatt times the time in hour. So the energy will be power will be 0.8 times the time is 2, which is 1.6 kilowatt hour. So 1 kilowatt hour is 10 cents. So 1.6 will be 16 cents. Okay? That's easy, right? So when you buy a new microwave or a new AC, new fridge, you have to look at that because it's a trade-off between the price and the amount of energy you're going to save given the power and given the cents per kilowatt hour. You have to do those computations because sometimes you say, oh, it's going to save you a lot of energy, but it costs so much money that sometimes it's not worth it. Okay, so another thing that you have to be aware of is that calorie is also a unit for energy. So the calorie that you are using in chemistry is lowercase. Uppercase calorie will be food calorie. Okay, so with the uppercase is food calorie. And one food calorie is 4,000 joules. Okay, so that means in food you have a huge amount of calories, energy. Very sad, sad. It's very sad, right? Okay, so one food calorie, you have one. I mean, give cookies to teenagers and then give them like hammers. See what's gonna happen. A lot of energy in cookies. So 1 kilowatt hour, it's going to be about 1,000 food calorie. Okay, and one food calorie is about 4,000 joules. And one lowercase, which is chemistry, is only 4 joules. Okay, so 1 kilowatt hour, the unit of energy, is about 1,000 calories. And I told you before, we human same we consume the same amount of a 100-watt light bulb. So in 24 hours Can you find how many calories do we need based on that conversion here? So 1 kilowatt hour is 1,000 calories. So in 24 hours, how many calories? How many food calories? So kilowatt hour, that will be the energy that we are consuming, will be the power, our power, right? Times time in hour, right? Which is how much? No, this is, sorry, I'm ahead of myself. This is kilo. So 100 watts in kilowatts. It's, yeah, 0 0.1. How many hours in one day? 2.4. So that's going to be 24. So 2.4, right? Kilowatt hour. So that will be the amount of energy that we are producing, losing in one day. Yes? Why is it 0.4? I don't know. I was seeing if you are paying attention. So 0.1. Is that correct? Okay. And what? So you know that 1 kilowatt hour is about 1,000 food calorie. So 2.4 kilowatt hour is how many calories? Right, isn't that interesting? That's what they tell you, right? So of course, about average, if you have insulin resistance, it's gonna be less, 1,500 calories. If you are young and healthy and an athlete, you're gonna need 3 times more, or you're gonna produce 3 times more. But it's on average about 2,000 calories, food calories. By the way, calories in, calories out doesn't work for the human body. It works for the machine, not so for the human body. It's much more complicated. Okay, so I'm going to leave that for a pop quiz, but the idea is that if you want to lose weight, you stop eating. Exercising, it's good, it's healthy, but it doesn't work that well. But you can do the math. You can do the math to show that because you have so much energy into food. Okay, and per gram of fat, or yes, fat in the body, there is 7 food calories. So if you want to lose weight, stop eating. Exercise is good, it's healthy, it doesn't work that well. Okay, horsepower. 1 horsepower means that, for example, a horse is able to lift 100 pounds over 330 foot per minute. Okay, so horsepower was defined as 33,000 foot-pounds, which is about 1 horsepower is about 1,000 watts. So you can be a horse, but only for a very short time. Okay, so that will be energy for you, energy units of energy, units for power. Okay, and then we have also interesting definition. So average power is the work over the time, or change in kinetic energy over the time. Now, if the force that is delivering, so it's a power is delivered, right? So if the power is delivered by a force and that force stays constant, doesn't change with time, so then we can say that the work is the force, the net force, or the force that is delivering the power times the displacement over time. Okay, so the force, if the force stays the same over the displacement, so the work done equals force times displacement, then you divide by the time, so you get the average speed. So that will be a very useful definition for average power. The average power is force if it stays the same, so acceleration is constant, times average speed. If it does not stay the same, when you are computing the work, you have to use that integral. Okay, force versus displacement, you have to integrate, you have to add up. Okay, so let's take an easy example. Let's use two ways to do it. First way, we're going to say average power is the change in kinetic energy over the change in time. Second definition, we're going to say that the average power is the force times the average speed. Okay, we can use two definitions for power. It's much easier now. It's going to be much easier for the rest of the semester. I think. If you have an equation before the test, that will be after the class. So force and work. Okay, we have the mass, 1000 kilogram. You have initial velocity is 0, final velocity is 27. The time elapsed is 10 seconds. So way number 1, the average power is the work done by the engine over the time elapsed. And then I can use the kinetic work kinetic or work energy theorem that will be equal to the change in kinetic energy over the time. And that will be 0.5. The mass, the final speed minus initial speed over the time elapsed. This is my screen. Is that my screen or is it something here? So you get what? 1000? No. You square the 27?
Oh, 36,400.
Yeah. Thank you. Joules. No. No. Joules per second. So it's what? Okay. Way number 2. I'm gonna say that the power is the force times the average speed. And in that case, the force does not change. And the force equals ma, F equals ma. And remember that there is this definition for average speed, which was the initial speed plus the final speed divided by 2, because the speed increases at a constant rate. So we just take the midpoint. Okay? Okay, so you just plugging in. So the average power is the force, which is mass. So mass, 1, 2, 3. Acceleration is the change in speed. So 27 minus 0 over 10. And the average speed is 0 plus 27 divided by 2. Right? And you should get the same thing. But this is true because the force is constant. The force is constant because the acceleration is constant. So then I can use that. Otherwise, I can't. Otherwise, you have to find the work, the energy transfer. So this is how fast energy is being transferred from system 1 to system 2. Any question? By the way, for the test, remember the loopy loop. Okay, so you remember when you have a loop like this, if it's upside down, so first of all, the centripetal force is always toward the center, right? So that means you need something really big toward the center. In that case, you're gonna have the weight, and then from the surface to here, you have the normal force, right? So in that case, it's good. But if you have a loopy loop the other way, like something like if this is here, so you still need a larger force toward the center. So you need a large weight, but which will be smaller. If it goes off tangent, like in the loop of doom, then the normal force equals 0, meaning it doesn't touch anymore, right? So it's important to remember that it's the larger force that provides the acceleration. So for this one, you have different ways to do it. But one way to do it is just to use the speed. Okay, so we can use the equation that power, the average power, is the force times the speed. And remember what I told you always to memorize that if something is on a slope, inclined plane, okay, going up or down, so let's say you go up or you go down. Not the Daytona Beach thing, okay, that's another thing. But if something is on the inclined plane, there is two components for the weight, right? So one component is mg sine, and then this component here is mg cosine. Okay, I told you to remember that. And then the weight, of course, here is straight down, but each component has a different job. And then, of course, here you're gonna have the normal force, which is perpendicular. Right. So when you go up slope and there is no friction, the force that you need to apply will be equals as mg sine alpha. Okay, that will be the force, your thrust. Okay, the thrust that you need to generate. That will be your thrust. That means you pushing on the bike, pedaling. So that will be your thrust here. How much force has to be against gravity? You are doing work against gravity. Okay, so if you go up slope, okay, so the average power will be the power you are delivering, the power that you are generating. It's always delivered by something, so the power you are delivering will be equals that force here times the average speed generated by you, because you have to work against gravity. You have a different way to do it, but that's one way. So in that case, mg but it doesn't say the mass. Oh, yes, thank you. So the average power will be 80 times 10 times sine what's the angle? So you figure out the angle times the average speed is 4. Okay? That's one way to do it. So 10%, it means this is 10 and that will be 100, right? 10%. So sine alpha will be opposite. Or we can use tangent to find. Right? Oh, does it say 6? Maybe it's 6. Oh, you're right, it's 6. Okay, it's 6. I didn't know. You don't have to do that. But anyway, you see how it's done. 6 degrees. Okay, so that will be your average power. The mass times 10 times sine 6, you write 6 degrees times the speed, 4. You can do it different way. Yes? Okay. You can do that. So here, do that on your own, especially if you want to be, if you're going to be an engineer, it's a good thinking for the brain. And you have the solution here. Lamborghini 657 horsepower Maserati. I think we are in the place in the world where you have the most highest density of Italian car. Expensive. Okay, let's take an example here. So it's a nice review because it's moving at a constant speed. So it's a dynamic equilibrium, which means the acceleration is 0, which means that everything up equals to everything down. So they want to find the power delivered by the motor, the tension here. The tension is from the motor. So they want to find the power of the motor or the power delivered by the tension. And you have the speed. So the first thing is to find the tension from the motor in the cable, find the tension, and then you multiply by the speed to have the power. Okay? So first, there is no acceleration. Up equals down. Don't stare. Do it, do it, do it, do it. So first you find the tension. So that's from the power, from the motor. Oh, it's like hooked. Okay, so everything up equals everything down in magnitude. If you do it this way, you don't have to do it this way. If you are doing it this way, there is no negative sign. So up, you have the tension. Down, you have the weight, which is, okay, you have to add them, times 10, 800 plus 1000, and you have some friction. So that will be the tension. Do you all agree?
Would not want look 4,000 against 8,000. It says that it retarded the motion.
So here, so this is retarding, but the load, the all mass is also retarding. So the weight is pulling down. So this is inside the bag. So you have to forget.
Stop.
No. So it's moving at a constant speed, but the acceleration is 0. This is my bag. So you have T up. You have the wave. Yes, yes. And you have some friction from the rails. So there's no acceleration. No acceleration means up equals down. Do you agree? Okay. So that will be to good. Newton. 22,000 Newton. And I can use one of the equation, one of the definition, the power delivered by a force. Okay, so delivered by the motor will be the force that generates that is the force from the motor, which is T, times the average speed in magnitude. It's a scalar. Okay, power is a scalar. It's always positive. There is no negative. I mean, you could if you are losing. So it will be 22,000 minus, no, times 3. Yeah, which is 66 kilowatt. So that's why you understand more about machine and things like this. 66 kilowatt. Okay, any question? Okay. And then they convert that to horsepower. Easily just 1 kilowatt is 1 horsepower. 1 kilowatt is 1 horsepower, so you can just about 65 horsepower if you do some approximation. Okay, and then if you want to do some calculus here, you can find the instantaneous power, and then you have to take the derivative of the work as a function of time. Or you can use work, you can use the power to find the work done between time 1 and time 2. You have to integrate over the time. And then we get to conservation of energy, which is super, super nice because it's going to be super, super easy. That comes from the book I was telling you, interesting. He compares in that book, that professor here, it's called Physics for Future Presidents. Sometimes it can be very surprising. He compared the energy delivered for the same mass of different systems. So chocolate cookies has 8 times more energy than TNT for the same mass. So you compare energy to the energy of TNT, dynamite. So 8 times more. That's chemical energy. Okay? If you give cookies to a kid, not a good idea, right? And then gasoline, fossil fuel, lots of energy as well. That will be chemical energy. It's inside the bonds. 15 times more than TNT. If you take atomic energy, like energy in uranium, for the same mass, you have about 1,000,000 times more energy that you have in fossil fuel. 1,000,000 times more for the same mass. So you need a lot of fossil fuel and you need a tiny bit of uranium for the same purpose. Okay. So okay, we did that. So again, this is the work energy theorem. The net work done on a system equals to the change in kinetic energy. Okay, so we did that. We already discussed that here. Do you think the force is doing any work here on what? On the spacecraft? No. Very good. It's a circular orbit. So that force doesn't make the spacecraft go faster or slower. It does not change its kinetic energy. It's perpendicular to the displacement. So there is no work done. Okay. And you see that it's perpendicular to the displacement, so no work done. If the trajectory is elliptical, so then yes, there will be work done because the spacecraft is going to change its speed, right? It's going to zero, zero, elliptical here, like Pluto. Pluto was demoted, which is very unfair, doesn't make sense, and it's very mean. 2006, it was demoted to be a dwarf planet, and dwarf not like an adjective, like a noun. So insult, it's very insulting. Dwarf planet. So anyway, okay, let's apply here. I'm going to do it two ways. You can do it two ways. You can do it the way we have been doing it. So net work equals change in kinetic energy. And we're going to find a new way to do it, which is conservation of energy. So here it has initial velocity, and we want to know how high it goes. You could also do it using kinematics. In 2006, they did it during the summer. So most of the people involved in that committee, they were summer professors. You know, summer, that's why you want to be a professor, because you have the summer off. I mean, kind of, if you're not doing research. So they were all on vacation. So that's when they decided in a very sneaky way to demote Pluto. Okay, so what is doing the work here? That will be the weight. So gravity is doing negative work on the athlete. Okay, so the work done by gravity, okay, on the person, it's gonna be negative work, right? Yes, absolutely. You can see that like that, right? Delta y or delta h. Okay, displacement is this way, the weight is down, so the dot product is going to be negative. Or you can say it's negative because gravity is trying to slow him down. Okay, so it's going to be mg times this, and that should be equals to the change in kinetic energy. Okay, so that's the work energy theorem. And you see that the mass goes bye-bye because it's in free fall, so the mass should not matter. It goes bye-bye. So minus the height. So we start the height from here, so it's 4.8 times gravity, which is 10, equals 0.5. Final is 0 minus initial speed. Oh no, did I do no, I did a mistake. I didn't read. Just to show you what you should not do. Yeah. So the displacement will be 4.8 minus 1.2. Yeah, I went fast. I saw this and I didn't see this. You have to read. Okay, so that means minus 3.6 times 10 equals 0.50 minus initial speed squared. Okay, so that's good now. So what do you get? 3,
8.48, so 8.5 really.
8. Okay, that's way number 1. Way number 2. So you have, so in that case, you see this is plus, this is minus. Okay, or the dot product. If you do the dot product and they are anti-parallel, the dot product is going to be negative. If they are parallel in the same direction, then it's going to be positive. Or you can say you are doing work against gravity because gravity is trying to stop you, to slow you down. And you need a negative, otherwise you're going to have a square equals negative. So the way number 2, we're going to say the total energy before equals total energy after. Okay, so we're going to say we have to, so if we use this way, we have to decide where is the potential energy equals to 0. So we decide of a reference level. So I say, okay, this is my potential energy equals to 0 here. And that will be initial potential energy. And that will be the potential energy here, which is the final potential energy. And this height here, delta H, is still 3.6. So we're going to use conservation of energy. So before as potential energy, kinetic energy. So this is only conservative force being involved. There is no friction, there is no thrust, potential energy after. So before, there is no potential energy. If I take it to be 0 here, you don't have to. You can take it 0 there. You can do that. You will get the same thing, but you have to decide. I take it here, but you can take it there. If you take it there, then it has initial potential energy. So that will be 0 plus 0.5 m initial velocity. So that will be the kinetic energy before equals potential energy after, which is mg times delta h plus kinetic energy after equals 0. And we get the same thing. Okay. Okay, we get to this famous equation. When you have kinetic and potential energy and you have free fall, you always get the velocity here equals to gh. Okay, so that will be conservation of mechanical energy. You start from the work energy theorem and you get to this conservation of mechanical energy. So it means the total amount of energy stays the same, but it's like the currency that is not the same. So it's like you have $600,000 dollars, and then some of it will be in euros, some of it will be in dollars. If there is no bank in between, so there is no friction, but the total amount of energy will stay the same. Does it make sense? So at the top, everything is potential, and then some of it will become kinetic, more of it will become kinetic, all of it will become kinetic energy. but the total amount of energy stays the same. Okay, let's do this one. So this is a projectile motion, and the way we used to do it is to decompose into the x component and the y component, and the x component, the velocity stays the same, and the y component is going to change at a rate of 10. And then once you have the final x and the final y, you can find the final speed. But we're going to do it a different way, easier. We're going to do it with we're going to do it with conservation of energy. So total amount of energy before equals total amount of energy after. Go, 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 go. We want to find that speed here. Energy is a scalar. So you can lose energy, okay? It can be negative, but there is no direction. Help each other, talk to each other. Okay, so we decide, maybe we want to decide that potential energy equals 0. So that will be the first step. You decide where is it equals to 0. Potential energy depends on the reference level. So that will be before. And that's going to be after. The mass should not matter because it's in free fall. Okay, so before equals after. So potential energy before. So m g times the height, which is 70, plus kinetic energy 0.5, the mass 38 square, equals after m g 35 plus 0.5, the mass and the final speed square. So free fall mass goes away. On the left you have 10, 70 minus 35. What do you get? Yes. Do you all get that? So you have to imagine like energy, it's like a reservoir. You have a reservoir, that level here stays the same. At the beginning, it has a lot of potential energy here, and it has a tiny bit of kinetic energy. So at the end, you're gonna have the same reservoir here, like a test tube or a reservoir, a recipient, and now the kinetic energy is gonna be more. Potential energy here, kinetic energy there, but this is the same level. Okay? So if you have a system like the pendulum, and that's a very famous demo. So if I remove friction, none, okay, don't want friction, go slow. So here it has potential energy, and then kinetic energy, and then potential energy. So it's swinging back and forth between kinetic and potential, but total amount stays the same. If you add friction, then you're going to lose to friction. Okay, I will show you next time what it does, but you see, you are losing to friction. So the total amount is the same, except now you are losing, this amount is going away. But the total amount is the same. See, and you don't get it back because friction is non-conservative. You don't get it back, it's lost. So there is this very famous, very famous demo. So Walter Levin was an amazing, I mean, he's still alive, but had some issues with MIT. So he had great demo, very famous demo. That's one of them. 52 pounds is a lot. Just you see what he did. All that energy goes into force times distance. If the distance is small, the force is huge, right? Destruction. So it was very famous. Now, not only you should not give it initial momentum, otherwise it's gonna kill you, but you should not duct, right? If you move a little bit, that's it. So there was this video and they removed it. It was removed from YouTube, but it used to be that when I see something, I download it. Good thing it's not in the US because yeah, she went forward. And it's good it was not in the US. In the US will be a lawsuit. It would be very bad. Now you can go from potential, kinetic, elastic. We have also elastic potential energy with a restoring force, right? So that's what you have here. It's a little bit slow, so I'm not going. Okay, potential. I don't know if you kinetic, elastic, potential, kinetic, elastic, kinetic, potential. Okay, the idea is don't give up. It's a nice message, right? One step down. Oh, okay. I didn't notice. So it must be lost because of air resistance, right? Oh, okay. So it's conservation of energy can be easier than using, Newton's second law. You should not what do you think? Should if you don't want you don't right? She should not duck. Yes, that will be very bad. And then, so here, just write down the equation. We are not going to do it all the way. Just lay out the equation. You go from 10 to 5, and you want to find the speed at 5. So it depends. You can take potential energy equals to 0 either at the level of water or let's take it at the water, but it's not that smart. You want to take it here, but let's say just it's so easy. Okay, so you want to find the speed here. So you can take potential energy equals to 0 here, which is in that case the height is 5, or you can take it here. So if I take potential energy equals to 0, that's going to be before, and that's going to be after, right? So before it has relative to here. So mg times 10 plus 0 has no kinetic energy. After relative to here, it's going to be mg times 5 plus 0.5 mv squared. And they should be equal to each other. So you find always the same equation, 2g delta. Okay? If you start from here and you hit the water, then the height is just 10, and the height is 0 here. So you should find about 10, and for the water it should be 14. Okay, so in that case, you have some thrust to begin with. So it means it's a non-conservative force. So what do I mean by this? Is that you can say, okay, let's say you can have some potential or let's say you can have all kinetic energy like the trampoline. So trampoline, it had all kinetic energy, and then everything turned into potential energy. But you can add work to the system. So you can start with a system here, right, with some kinetic energy. Let's say it has some kinetic energy to begin with, and then you can add some work to it. So you are filling the recipient, the reservoir of energy. You are transferring energy. So that energy can be transferred because you are applying a force, or it could be because you are burning fuel. So once you add energy to the system, then all that energy can go into, some of it can go to potential energy. Let's do that in red, some potential energy, and some of it can be in kinetic energy. So this is non-conservative, okay? So you have a system, you can add some work, so that will be before, and then that's going to be after. Okay, so example will be that thing here, like skateboarding. You see, let's say you start, let's say you start with some kinetic energy, you pump. Pumping meaning you are doing some work over a distance. So you're gonna add to the initial kinetic energy, and you end up all the way up with some kinetic maybe and some potential. Okay, so even if a system has initial kinetic energy, you can add to it. So when you go down like this, you see you apply a force of gravity over a distance, you're adding some energy to it. Or you can remove energy if there is friction. You can remove from the system, right? So for example, in that case, you are adding chemical energy. So you start with 0 speed, you add some kinetic energy, and you will end up with some potential and kinetic. So if you want to do this one, so you are burning fuel. You are burning fuel. So this is chemical energy. So you have your reservoir. The reservoir was empty, and you add some work to it. So the level is not going to change. It's going to be the same level, except some of it will be kinetic and some of it will be potential. Okay, so the work here is 425 joules. So that will be your level. 425 stays the same. Some of it will be, so here potential equals 0. Some of it will be potential, so 0.2, the mass times 10 times the height. And some of it will be kinetic, 0.5 times 0.2 times the speed square. When you add them up, it has to be equals to 425. It's easy to understand if you imagine a reservoir, like a beaker, a huge beaker. Beaker is 425 joule, and then some of it will turn into potential energy, some of it into kinetic energy. When you add them, it will be the same amount. Agree? But the potential energy, you have to decide of a reference level. So if you keep in mind this, and that will be the answer. If you keep in mind this image of a reservoir,